Good morning, everybody. This is lecture 13, but I just have to finish off a little bit from last class before we move to actual lecture 13 uh, presentation. So, what we were discussing last time, so we were almost done with your Prim's algo. So, okay, let's go over the runtime of Prim's algorithm. So what we are doing in Prims, we are starting with the source and we are maintaining a queue, and in that queue we are putting the distance, or we are actually putting the edge. So just a second. So if you see here, this part, if you look at what we do is we extract the minimum from the queue, and based on that vertex, whatever edges are going out of the vertex, we see if the existing distance to the other vertices is less than the distance of those vertex from this u we are considering. So we are at u, so we'll check all the edges that go out of u, and we see if this x, y, and z, if the existing distances of these vertices in the queue, if it's less than this distance here, then we keep it. If it's more, then we replace it with this. So if you look here, what we are doing, we are in this line, we are comparing the weight of the edge u to x, u to y, u to z with the existing key value for that vertex. Okay, and accordingly we update. If we find a smaller value, we update it. So this is important. Just look at this line and remember what we are doing exactly. And the next algo that we do, that has a slight modification here, otherwise it is the same as Prim's algo. So first of all, let me just remove this. Okay, so the inner loop here, we discussed this last time, how for every vertex, when you do extract min, you have to readjust the heap. So log v, and for every vertex you're doing this, so v log v, and then for every edge you will do this relaxation. And this relaxation, we call it relaxation in the sense, if you find some distance which is smaller than the existing one, then we will replace it, and that will also cause your heap to readjust. So for every edge you will do it. So how do we know that we do it for every edge? I'll just come to that. So for every edge you'll do e log v, and for every vertex, obviously whenever we take out the vertex, we will be readjusting the heap. Okay, so if you look here, okay, when we are starting here at vertex E as our source, okay, so when we put the distance of, or the key value of E as 0, that means we will extract E first. When we extract E, we will update these two edges, okay. Then whichever is the minimum of the two, which is H, we will take it out in the next step and we will update these two edges, right? Then let's say B is the next minimum, we'll update these two edges. Then let's say A is the next minimum, we'll update this edge. So when we reach at A, we update this edge, which I just marked in yellow, but we don't update this edge again. In the sense, we don't go in the reverse order. So for, if you look at it, for every edge, when you take out, let's say C, you will update these two edges. I don't update the edges. What I mean is, I update the distance from C to D or C to F if the weight of this edge is less than the key value that is held uh, in your heap. Okay, and then when I extract F, so if you see all the, for when you are going through this entire process in that loop that I just marked, I am visiting each edge once. So for every edge, when I make a change, if at all, to the key value of any vertex. So that is how I get E log V. And this E log V is, and this E log V is, it takes care of all of this because for every edge, we are doing it once only. So it's, if you look at this loop, this is how you have to understand this. Okay, so this is your Prim's algo. Hmm. Okay, just accidentally closed it. So now, before going to the next problem, so for Prim's algo, whatever you are using to store your queue, how you are making your queue, which holds the key values and from which you extract every vertex, that will decide your runtime. So if you're using a simple linear array instead of a heap, then obviously you have to take into consideration updating this array every time. So it's, if it's an array, you'll take at least on time to scan through the array and take the minimum out. If you're not in heap, you just go and you take the root and the heap readjusts. Here, if you have everything stored in a queue, you have to scan the entire queue or the array and you have a runtime of on. Okay, so then accordingly your runtime will change. It changes to ov square. So that's all. You can just go through this algo with, there are some minor changes. Instead of the heap log v value, you have v square now. Okay, so the next example that we are doing for greedy, we have already done the traveling salesman problem. What we did it using dynamic programming, and we got the ideal or the optimal solution. So now we are trying to go do the same problem using a greedy algo, and we are hoping to get a good solution, maybe not the best or the optimal solution. So what would be a greedy approach when you are starting solve a traveling salesman problem? You are at a city, you know the entire let's say map is in front of you, you have all the distances for all the cities, but currently you are at a particular city, and from there, what is your greedy approach is to go to that city which is closest to you. So irrespective of what other distances are, so you visit the nearest city, or you visit the city which is at the smallest distance from the current city, and you keep doing it. So at every step, your greedy approach is that you select the city which is the nearest to you, and you do that and you get some solution. So if you look here in this graph, what we have done, you are, if I start at A, I have distances 1, 3, and 6 going to B, C, and D. So I'll take this distance 1. Now I'm at B. B has a distance of 3 to D and 2 to C, so I'll select this. And I'm at C. From C, the shortest distance is 1 to D. And from D, you go back to 1. So the total cost is 10. But the optimal cost is 8. How do you get the optimal cost? You go from A to B, 1, B to D, 3, that makes it 4, D to C, 5, and C to A back 3, so 8. Okay. So what they have calculated is like a ratio of how close you are to the optimal solution. Uh, just 1.25 when you calculate the your your total distance versus the actual or the optimal distance. Now, okay, what we are doing here is we are selecting the nearest city every time, but when we are at the last city we are bound to go back to the starting city no matter what the distance is, because we have chosen it this way. Now we don't have a choice. So if you see, returning from D to A is the most expensive, because you have B to A. If you say see B to A, if B was the last city you visited, then B to A is 1. If C was the last city you visited, C to A is 3. But D is the last city you visited, and you see the 6 is the worst distance you can have on return. But when you chose this way, you reach D, you don't have any option of retracting. So you just have to go back to A because you have to complete your tour. Okay. So what if this distance was this big? So normally what they do is, it won't be this big obviously. Why? Because it can be this bad. You can have the worst distance from D to A and get messed up. Your solution will get messed up. But if your graph follows Euclidean geometry, you know that sum of the two sides of a triangle is always greater than the third side. So the third side will be within the limits of the sum of the other two sides. So in that case, the distance, if I have an edge, if I have, let's say, 6 and 5, this is not going to be 10,000. So that won't be possible. So if your graph follows Euclidean geometry, even, let's say, it just touches the Euclidean geometry rules, then something like this is highly unlikely. Okay. So what we do is, now with the approach that we took still can give us a problem like this, where you have to return via the path which is the worst path in the graph. Okay. So they use something which we call as an approximation algorithm. You'll do more of it, not in bachelor's and maybe master's. So approximation algo is like, you approximate the solution. You'll not still get the best solution, but it will give you a good enough solution. So the approximation solution they use for traveling salesman problem is using the minimum spanning tree. Because once you have the minimum spanning tree of a graph, you know you have selected the least cost edges. Okay. Because minimum spanning tree selects the least weighted edges to connect the cities. So you have a graph. If you have a minimum spanning tree of a graph, you have all the cities connected with their least distances, right? So somewhere you have already chosen something which is good, in the sense which seems to be something which will give you an optimal or a good distance. Okay. So let's see what happens if we do that. So what they do is, they first construct a minimum spanning tree of the graph. So obviously it is like a tree. You cannot find a cycle or a tour in the minimum spanning tree, because that's not how a minimum spanning tree is supposed to be. It is going to be a tree. So you're not going to find a cycle. And what we need in a traveling salesman problem, we need a cycle, Hamiltonian path. You start at a city, you go through all the vertices, and you come back at the same city. So what they do is, they first construct a minimum spanning tree of the graph, for the same graph for which you have to find the traveling salesman problem. Then you start at any vertex in the graph and you perform a depth first search walk. Okay, we're going to do depth first search again in detail, but you have a brief idea what is a depth first search. You start at a point, you go to the next point until you have somewhere to go to. You keep on moving ahead, and once you are stuck, you don't have any other vertex to go from there, you retract back one step and then see is there any other path you can go to. Then you go there and you come back. Okay. So we will perform that kind of a walk in our minimum spanning tree, starting at any vertex, and then we will list all these vertices in order. And Obviously there'll be some repetition, because when you retract from a vertex to the previous vertex, you are repeating a vertex in the sequence of vertices you visited. That is how it goes for DFS. So we will remove the repetitive vertices, and then that will give us a Hamiltonian circuit. So this is a graph, and this on the right you have the minimum spanning tree of the graph. Okay, you can use Kruskal's algorithm to find the minimum spanning tree. 4 is the least distance, then you have 6, then you have 7, and then you have 8. So we found the minimum spanning tree for this graph. Now let's say they have started at A. So what does a DFS walk mean? DFS walk means I go from A to B. Okay. From B, I have two options, going to D or to C. Let's say if no order is prescribed, you go to C. After C, there is nowhere to go. So you will retract back to B. Okay. These are my stopping points. From B, there's only one way, you can go to D. And from D, you can go to E. Okay. So this is my DFS walk. It is listed here. A to B, B to C, B to D. After C, you're actually coming to D, and D to E. So AB, BC, then CB, then BD, DE. Okay. Then how do you come back from E? E to D and D to B and B to A. So you started your walk from A and you came back all the way to A. Okay. Okay. Let me just explain the DFS on this graph. Okay. If I start at A, I go to B, I can go to any vertex. Let's say I go to E. So after E, I can go to D. From D, I can go to C. From C, I cannot go back to B because it is already visited. So I'll go back to D. From D, I'll go back to E because there is no more unvisited vertex. From E, I'll go back to B. And from B, I'll go back to A. So it is my DFS walk for the graph. And when we do the same thing here, I go from A to B, B to C, then from C to B, B to D, D to E. So I have to return E to D, D to B, and this. So this is my walk listed here. So these are the vertices I have followed. So I have A, B, C. There's a repetition B, I'll cut it off. Then I have D, E. Again, D is repeated, B is repeated, and A is required at the end because I want to complete the path. I want to complete the tour. So I use minimum spanning tree to complete my tour. Minimum spanning tree does not have a cycle. We are generating a cycle by performing a depth first search walk. And if you see now, the answer that we are getting this A, B, C, D, E, A. So let me mark it on the graph. A, B, B, C, C, D, D, E, and E, A. So this is my Hamiltonian cycle, or this is my tour. And the cost of this tour is 10, 22, 41. Okay, you can try this using dynamic programming and see what you get as the optimal solution. Okay, so I'll leave that as an exercise to you. This is an approximation solution. It might give you the correct result or it might not, but it will be very close to your solution. So let's go up here. Okay, let's say we apply this uh, approximation algo to this graph. So what is the spanning tree? Let's first make a spanning tree of this graph. A to B, D to C, and then B to C. So this is our this is our minimum spanning tree for this graph. So I'll start at A. This is my DFS walk, A to B, It's very simple here. B to C, C to D, D back to C, and then back to B and back to A. So A, B, C, D. Then I cancel the repetitions. So I get A, B, C, D, A. So I'm getting the same thing using my approximation algorithm. So again, I'm getting something which is close to the actual or the optimal solution, but I'm not getting the optimal solution. And it's not because it's an approximation solution, you don't expect the perfect solution. Okay. Aman, can you check? I'm getting some noise.
Yes, mom.
किसी के इससे no, there is some noise. Just see किसकी mic on
Okay,
है.
okay.
Let's see if
हाँ,
there's. Okay, fine.
अभी तो सबका ऑफ है.
ठीक है. Okay, moving on. This is your. This is now your actual lecture 13. So the next. Mhm. The next greedy algo that we will do is your. Okay, is it visible? Lecture 13.
Yes, mom.
Okay. So the next greedy algo that we are doing, we still have many graph algorithms to cover, but this one is greedy, so we'll cover this first. So the next algo that we are studying is for single source shortest path. So there are many graph problems that you will encounter. You can have all pairs shortest path, single source shortest path, or just um, single source to a particular source you want to find the shortest path. So the algo that we are studying is for single source shortest path. So you select a source and you get the shortest path from this source to all other vertices in the graph. And the algo that we are using is Dijkstra's, and it is a greedy algo. And it's pretty much similar to your Prim's algorithm, but there is a minor difference. So we want to determine the distance from S to all the other vertices in the graph, and the distance should be the shortest distance. So it is also known as the shortest path tree to from you start at a root which is your source and then you go to the uh, to go to all vertices and find the shortest distance. So what we need to take care here is in prims when we updated the distances of when we updated the key values because we found an edge which is shorter to a particular vertex, we never stored the parent of that vertex. So parent means I want to because I want a path, I want to keep a track of if I have updated the key value for this particular node, which neighboring vertex led to that, which will give me the parent. So we'll come to that in a while. So you have to construct, if you have a source, you have to construct shortest path from source to. So sometimes S to A can be a shortest path from S to A, or it can be SBA can be the shortest path. Or S to D can be like a direct shortest path, and then S to D to E can be shortest path to E. So we have to find all these pairs. So if there are, in this case, we have 7 vertices and one source. So we have to find 7 paths from S to all these vertices, and they can be same or they can be different. So Dijkstra's algo, normally it works on graphs with non-negative weights. Okay, we'll come to that in a while. Before that, if you have a shortest path from S to V, okay, as given in this. So there is some shortest path from S to V and it goes via T. So T is a vertex which comes in the path. There can be more vertices here. Okay. So If you say that S to V is the shortest path from S to, this is the only shortest path available, then S to T will also be the shortest path, and T to V will also be the shortest path from S to T and T to V respectively. Because obviously shortest paths will be made up, the fragments of these paths will also need to be the shortest to actually make the entire path the shortest path available for a particular. So Dijkstra's algo is named after a, you can say, a computer scientist. So his name was Vibes Dijkstra, and this is some information about him. I just wanted to. He has also received the Turing Award, which is supposed to be a prestigious award for computer scientists. So, okay, a little bit about him. So let's come to the problem and the algo first. Okay. So what is Dijkstra's algorithm? It is a solution to the single source shortest path problem in graph theory. So in graph theory, you'll study a lot more about graphs and different algorithms. It works on both directed and undirected graphs. So what is a directed graph? If you have an edge between two vertices, if this is U and V, if this is an edge, it is kind of supposed to be a bidirectional edge. You can go from U to V or you can go from V to E. But if you have something like this means there is a path from U to V, but there is no path from in the reverse direction. So this algo will work on both directed and undirected graphs. Okay. So if we have a graph, this is how we represent a graph. It is a set of edges and a set of vertices, and all the weights need to be non-negative. Okay. So that is the requirement for Dijkstra's algo. You'll see there is, we have other algos that can take care of negative weights, but then there is a problem of having a negative weight cycle. So we'll come to that once we do more algorithms. So this is the requirement for your Dijkstra's algo to work. Okay. So what does this algo do? It is very much similar to your Prim's algorithm, but there is a difference. So first of all, you initialize the distance of the source to 0. Okay. So again, we have a priority queue which has all the vertices of the graph. We initialize the distances of all vertices to infinity, and only the source, we select the distance as 0. So this is our source S. The distance of the source is 0. We are starting at distance 0. For all other vertices, we set the distance to infinity, just like we do in Prim's algo. Then we have a set S of all visited vertices. So if you have already visited the vertex and uh, um, looked at all the distances or all the paths that this can offer, the distances of all the paths that can go via S. And if you have extracted, if it's already visited, it's there in the final answer. And then this is a queue which will hold all the vertices initially. All the vertices are associated with the distance, which we have already done. So while this queue is not empty, what we do, we extract the minimum from the queue. So what will get extracted first will be your S, just like in Prim's algo. So whatever we extract U, we add it to our solution, the final set, the set of visited vertices. Now, once you extract a vertex, for all the neighboring vertices of this U vertex, we do this calculation. Okay, this is also known as relaxing the edges. So, what do you mean by relaxing the edges? If the distance of U is the one that we extracted just now from the Q, if the U has a distance associated with it, for example, U is equal to S, so the distance is 0. So if the distance of U, it might not be the source, it might be some other vertex X which is at a distance of 2 from the source. If it's like this, so you were at a source and then you have some vertex y at a distance of 2. Okay, now y has two neighbors a and b. So for every neighbor of y, so a and b will have some distances associated with them. What I am checking is the distance, I just write d, distance of a greater than the distance of we are here. Okay, this is what we have extracted. Distance of y plus, I just give a number here, the distance from weight of the edge y and a. Okay, okay. If the distance, this d1, is greater than this distance y plus 3, that means if you can, a1 can be approached by a distance of d1, and if you can reach a1 via s to y and y to a, the distance of y plus this 3, and if this distance is less than the distance that a is already has stored in it, then you will update, you will change the distance of a to this distance y plus 3, only if this is less than the existing one. We'll just see in an example. Okay, so if you have changed the distance of a because of y, because you thought, not you thought, you actually saw approaching from y is shorter than d1, that means a already, you were able to approach a through some other vertex. Now you are actually coming to a from y, so that means the parent of a is y. So actually here, if desired add a trace back, you also have to update the parent of parent of v equal to u, according to this code. If approaching this, if the if approaching v is shorter through u, then you will update. Okay, we'll just see that in an example. So if if the new if you, that means if you have found a new shortest path, then you will set the path like that for that particular vertex, and you'll do this for all the neighbors of the every node that you extract from the queue. Just like in Prim's algo, we extract a node, then we see if from that node to a particular to the neighboring node, if the distance is less than what is already there, you update. But here we are not only in Prims, you will just take care of this edge. Okay, you'll see if this is u and this is v, whether this is smaller than what distance is actually stored for v, or what key value is actually stored for v. But here we will, we are checking whether whatever path you took to come to u, that plus this is less than the distance or the key value, because we are looking for the shortest path from some source s to your, let's say, x. Okay, so we'll just see in an example. Okay, so this is our example that we will see today. So initially, what is the first step? Similar to Prim's algo, you initialize everything to infinity, and your source is a, so the distance of a is 0. You will also, side by side, in this example they've not given the parent of uh, all the vertices. So if we are listing them in order, the parent of all of them is nil. Okay, nil nil for now, because there's no path, so all the parents are nil. Okay, the parent vertices, that you can have a array or a matrix, and everything is nil. So you go, once you extract a from the queue, you extract a, you visit all its neighbors, and you see if the distance of a, 0 plus 10, is it less than infinity for b. So to come to a, you need a distance of 0. Is 0 plus 10 less than infinity? Yes, that is true. So you will update this distance here to 10. 10. And you'll also update the parent of B to A. Initially the parent was nil, now it is A. So similarly, you do the same thing for C. Is the distance of A plus 3 less than or equal to infinity? Yes. So you see both are updated here. D and E are not connected directly, so nothing as of now for them. You have extracted A, so that is in your list of vertex that you have already visited. Okay, now next, out of B and C, C is the one with the least key value. So you will select C. Okay, so C, once you select C, you have to see all the neighboring nodes of C, and you have to relax it. Relax means you have to see if relaxing means you have to see if the distance of that node. So what are the adjacent vertices? DB. If this is greater than distance of C plus the edge from C to B, that is 4. So what is the distance of B? It is 10. What is the distance of C from A? That is 3 plus 4. So this is 7. So 7 is obviously less than B. So we had selected B having a path from A. The parent of B was A. But now since this is true, what you will do, we will update the distance to 7 and also the parent to C. Now basically the shortest path to B is from A to C and C to B. It is no longer 10. So you have updated the parent and you have also updated the distance. So you'll do the same for D. D is at a distance of 8 from C. So the distance of C is 3. So what is the update? This is changed to 8 plus 3, that is 11. And E is changed to 5, 3 plus 2. Okay, so next, these are updated based on the edges. For all the edges or for all the
Waste.
for all the adjacent vertices, you will update the distances. So if you look here, so you're doing it for all the neighbors. Okay, now this is updated. All the three distances are updated. You will extract the next minimum, which is E. So E is extracted and then you update the distance. So no, nothing is updated because the distances are already less than the distance from E to those nodes. Then you will extract 7. Once you extract 7 means B. B to D is, if you add the distance, 7 plus 2 is 9. So this is the red arrows. This is smaller than yes, the arrow is in the wrong direction. This red one. Okay. So C is, there is an edge from B to C also, but then C is not in the queue, so it cannot get updated. It is already visited. So since it's already visited, you will not update it, even if the distance was less. Okay. So this is basically, this gives you the final shortest path distance from source to all these nodes. Let's just put them here. So the distance of A is 0. The distance of B is 7. We saw the parent of B is C. So it goes like this. Then the distance of C is 3, which is obviously like this straight away. The distance of D is 7, 8, 9. And the distance of E is from it is through C. So we have to store the parents as well. Whenever we are relaxing and something gets updated, the distance gets updated, you also put the parent in a separate array. Store the parent of each vertex. That will help you trace the path. So the simplest implementation, if you're not using a heap, you are using an array. So you have to scan the array for the least key value vertex and then extract that. You can use an array, and obviously you have v vertices, you have to scan them. Just like for prims we got v square, we will get v square here. But if the graph is sparse means it doesn't have as many edges. The graph is connected, but then there are less number of edges. So for any graph you can have how many edges, we discussed that. So if you have 3 nodes, you have 3 square. At the most you can have 9 edges, including a self loop. So if it's a fully connected graph, not connected as in it has all the edges, it can have up to v square edges. But normally that's not the case. So if it's graph, then storing it in an array uh, would be a little more heavier in implementation. So we can use a binary heap or a priority or a priority queue to store only those, to store the edges, and then you'll have a log v time, because if v increases, your v square also increases. So if v increases, log v, obviously log v is always better, so log v is there. So the runtime is e plus v log v. So I'll just go over the algo again. So for as with greedy algos, we need to make sure, so there's something known as checking the correctness of the algorithm. So for that, you need mathematical proofs to show that what you are claiming, that this will give you the shortest path to all the other vertices, whether your claim is true or not. So you can use many mathematical lemmas. Lemma is like when you prove a theorem, you conclude some things from that. So one is the triangle inequality, which we just talked about. If using that in mind, the shortest path between u and v obviously goes through some vertex in between vertex, like I said. So if that in between vertex is x, the shortest path from u to v will be the shortest path from u to x, and then the shortest path from x to v. So the subpath of any shortest path is itself a shortest path. Okay, so you don't need to go to the correctness part, you just have to go to the analysis part. Okay. So we'll just go over the examples and I'll go back to the algo. So where is Dijkstra's algo use? You have a network, you want to find the smallest, uh, there are many routing paths available for your packets, you want to find the shortest one, or shortest one might not always mean based on the distance of the switches. The cost of the edge can be anything. If you are tracking the network statistics at a particular point of time, you see that, just like in your Google Maps, you see a red line somewhere, you mean, it is congested. So your shortest path, in terms of, maybe not in terms of distance, in terms of the time you take from going from one place to another, it will show you alternative paths or alternative shortest paths in terms of distance. If your current shortest path is heavily loaded with traffic, and obviously it's going to take you more time, clear that off. So similarly for networks, we talk of congestion in networks. So if there is congestion in any part of the network, you look for other shortest paths, you eliminate that. There's another algo actually, which is known as let's say Dijkstra's algo with a bottleneck. So you know where the bottleneck is, so you try to eliminate that, and without that you try to find the shortest path. So we're not doing that in this course, but you probably won't might do it later somewhere in maybe networks or further on. So this is the application of Dijkstra's algo. So just go back to the algorithm. Okay, so let's first go here. So what is the runtime? It is e plus v log e. So again, it is e plus v log v was the runtime of Prim's algo as well. So you are doing the same thing in this algorithm. You are So you are extracting, when you're extracting a vertex from the queue, you are readjusting the queue, and you will be doing it v times because you will extract every time. And in this case, in this loop here, for every vertex, you are considering the edges that are connected to it, and you are relaxing. So when you're relaxing all these nodes which are adjacent to v, you might update the distance of all these. So this distance, this distance. So how long, how much time does it take? It takes log v to readjust the heap. And how many times will you do it? I showed you for prims. You do it once for every edge, right? So it is e log v. So that's why it comes to e plus v log v for Dijkstra's algorithm using a priority queue. So e plus v log v, or e log v plus v log v, is the total runtime of Dijkstra's algorithm. Okay. Now, this is another example. Just do it quickly before we finish the class. I just do it on my. Okay, let's do it here. We have a box prepared. I want you to do it on your own. I'll just do it roughly. So, if S is our source, this is my initial. In my first round, this is how I set the distances. Now I extract S from the queue. I just circle it. Once I extract S from the queue, I have to update all the vertices adjacent to it. I have to relax all the edges. So A is at a distance of 1, B is at a distance of 6, C is at a distance of 3, and D is not connected, so its distance will stay as infinity. So I have selected this. Next, I will extract A because the distance is 1. So I am here. So A is connected to C by a distance of 1. So the distance from S to A is 1. 1 plus 1 is 2. So we will update it. Then A is also connected to B by a distance of 4. 1 plus 4 is 5. So this will also be updated. So the parent, I'll write parent of A is S. Currently, the parent of B is A, and initially it was S, now it is A. And A to D is also connected. So 1 plus 4, 5. So parent of D is also A. Okay, 5 to 5. Now the next node with the least key value is C. So once I am at C, okay, C has two outgoing edges, to B and to D. So the distance of C is 2. 2 plus 2 is 4 for B. So this will get updated, and the parent of B will get updated to C. C plus C to D is 1. So 3. So again, parent of D gets updated to 3. Now next, D will be taken out of the queue. From D, you have a distance of 3 to B. So 3 plus 3, 6 is not less than. So uh, nothing gets updated. Okay. So next you take this. So if you follow the parent of B is C, and the parent of D is also C. So this is your shortest paths will all go through S to A to C, then C to B, and C to D. So this is your uh, Dijkstra's algorithm. I hope I did not miss out any edge. Okay, so similar to prims, but in prims you don't add the previous distance when you're looking at this edge. You just look at this edge because we are looking to add the smallest edge. Here we are looking to we have a shortest path already to A. We are looking to add the shortest distance to this shortest path so that we can make a shortest path to the adjacent vertex. Okay, so this is your Dijkstra's algo. This is one of the last ones of greedy algorithms for graphs. We'll do one more greedy algo in the next class, and then we'll move to all simple graph algorithms. So any questions in this? No questions? Okay, Aman, have you taken the attendance?
Ma'am, doing.
Okay.
Done, ma'am.
Done. Okay. Okay. All right. You have another class after this?
Yes, ma'am. Microprocessors.
Okay, fine. All right. Thank you.